Well, in this video, I'm going to go through the AQA AS-level Chemistry paper. It's paper 1, and it's the 2017 paper. I'm going to do it in 2 halves. I'll do the first half of the paper and the second half in another video. Okay, so the first question is about electronic structure. So I've got the periodic table there. The full electron configuration for each of the following species: chlorine. Okay, so chlorine, we've got here, obviously in the periodic table. So we've got a full 1s shell, that's full up. We've got a full 2s. We've got a full 2p. We've got a full 3s. Okay, so I'll write that down. So we have got 1s2, 2s2, 2p6, 3s2, and then we get to 3p. Now in the chlorine atom, we are going to have 1, 2, 3, 4, 5 electrons, but it's the ion, it's got an extra electron, so it's going to be 6. So it's 3p6. Right, the Fe2 plus ion. Right, so just get ion. So iron is here in the periodic table, in the D block. Right, so we have got, once again, a full 1s shell in red, a full 2s shell in blue, a full 2p shell in green, a full 3s, a full 3p, and then we start filling up 4s, and then we're going to have 1, 2, 3, 4, 5, 6 electrons in the D shell of the iron atom. So let's write that down. I'll do the iron atom first of all. So it's 1s, 1s2, 2s2, 2p6, 3s2, 3p6, 4s I should put there because that's slightly higher energy once you get some electrons in the P, and then 3d6. Okay, now to form the Fe2 plus ion, you've got to lose 2 electrons. They are lost from the 4s shell. That's slightly higher in energy now. So it's 3d6. Important to realize that it's not, you do not lose electrons from the 3d, you lose it from 4s. 1.2, the third ionization energy of manganese. You need an equation for that. So it's third ionization is going to be losing the third electron. So it's already lost 2. So it's an Mn2 plus ion. Gaseous, of course, has got to be the symbol. And it's going to lose 1 more to form Mn3 plus and an electron. Okay. Okay, which of the elements, magnesium and aluminium, has the lower first ionization energy? 3 marks for this. Okay, so let's just let's locate those 2 elements. Okay, so we have got, so you can see we've got magnesium there. Okay, and we see the last electron in magnesium is in the 3s shell, and aluminium here. Now the last electron in aluminium is in the 3p shell. So in the first ionization energy, you're going to lose it in the aluminium from the 3p shell, and so that's going to be lower. This one is going to be lower because the electron's coming from 3p, because 3p is slightly further from the nucleus. So you're going to be slightly higher in energy. So that's why the first ionization energy is a bit lower. Okay, so that will give you your 3 marks there. Okay, so this is about isotopes as measured in the time of flight mass spectrometer. Okay, ionization was by electron impact ionization, so you're going to form positive ions here, right? The spectrum produced showed 3 peaks of the abundance shown there. Give the symbol, including the mass of the ion that would reach the detector sample first. Okay, so right, so we know that every ion gets the same kinetic energy given by half mv squared. So that means the bigger m is, that means the v's got to be lower. So the big ions are the slowest. The heaviest ion is the slowest. So the lightest ion is the fastest. So it's going to reach into the detector first. So it's this one here. So it's going to be Ni58. And don't forget the plus because it says it wants the ion. Yeah. Okay. Now, calculate the relative atomic mass of nickel in the sample. Well, that is pretty straightforward. All we've got to do is, let's get rid of this. So we multiply the abundance of each ion by the mass of the ion. So 58, and we're going to have 61%. We need to do, so let's just do that as 0.61, makes it quicker. And then plus 60 times the abundance of that one, which is 29%. That's 0.291 plus 61 multiplied by 0.099. And that gives us an answer of 58.879. Right, now it says it to give to 1 decimal place, so 57. So that should be 58.9 to 1 decimal place. That's quite an easy question there. What they seem to be asking more frequently is they give you the, they sort of get to do it backwards, they give you this value and they'll give you the abundances of one of them and you have to work out the abundances of the other two. So that question is a bit on the easy side. Okay. Right, energetics. State symbol, an equation including state symbols for the reaction, the enthalpy change equal to the formation of iron 3 oxide. Now, iron 3 oxide is that compound there. You can see it's got an oxidation number of +3. So that's going to be 2Fe, solid, is the standard state of iron, plus 1.5 O2, standard state of oxygen, obviously is O2, gas. And that's going to give us Fe2O3, and that's a solid. So you need the state symbols there. So that would be delta HF. Okay. Now, it gives us delta HF values here, right? And it also gives us the enthalpy change for this reaction. And it says use the data to calculate, we need to work out delta HF for carbon dioxide. So it gives us delta HF for everything in that there. It gives it as for iron oxide, carbon monoxide. It doesn't give it as for the carbon dioxide. And of course, the standard enthalpy of formation of iron in its standard state is 0, so you don't need that. Right, now here's the equation. Now we're going to have to use a Hess's law energy cycle. And what's the third thing we usually put down? If we're given delta HF data, the third thing to put down in the cycle are elements in the standard state. So I'm going to write that down here. So that would be iron, 2 ions. We've got 6 oxygens there, so it's 3O2, sorry. 3O2. And 3 carbons. Okay, should put state symbols there. Solid, gas, solid. Right, and this red arrow, and do that one in red and do this one in green. The arrows go up because we're forming these compounds from the elements in their standard states. They come out green, that stays red. Okay, so let's see for the red arrow. What we're doing there, we're forming 1 mole of iron oxide, iron 3 oxide, and it gives us the value there of -822. And we're forming 3 moles of carbon monoxide, which is -111, so that's 3 times -111. Right. Let's add all that up. We get -1155 on for that red arrow. Let's do the green arrow. What we're doing there, we are forming the iron, obviously that's going to be 0, and 3 moles of carbon dioxide. Let's call that 3x. So let's say x is equal to the delta HF for carbon dioxide. Right. And they tell us that this change here is -19 kilojoules per mole. Right, so we want to, Hess's law shows us that -19, what we can do is we're going to go against the red arrow and with the green arrow. Right, we're going against the red arrow, so we have to change the sign to a positive here. So that's going to be +1155. We're going with the green arrow, so that's going to be, keep the sign, so it's plus 3x. Let's rearrange that. Let's do rearrange that then, so we get 3x is equal to 3x is going to be equal to minus 19 minus 1155. So 3x is equal to minus 1174. So x is equal to minus 391 kilojoules. And that is our value for delta HF for carbon dioxide, minus 391 kilojoules per mole. Okay, so that is a one Hess's law cycle. And right, the next question, right, is right. So it gives us here some enthalpy data here, and it says use the data to calculate the bond enthalpy for NH in ammonia. Right. So it's essentially, well, what have we got here? Well, that's delta HF. Well, 2 times delta HF for ammonia. That one there. Here, this is the bond enthalpy. Right. This is the bond enthalpy essentially, isn't it, for the nitrogen triple bond, and this is again the bond enthalpy for the hydrogen single bond. Right, so if we're thinking what kind of cycle do we want, well, we've got bond enthalpies. It's a good idea to write down here the gaseous atoms. Okay, so I'm going to have 2 nitrogen gas atoms and 6 hydrogen gaseous atoms. Just to remind ourselves what the bonds are like here, so I'll just sketch it in. So we've got that, and we've got 3 times of those, and here we've got 2 lots of ammonia. Looks like that. Okay, so with this kind of energy cycle, I usually, when you've got bond enthalpies, break everything up into the gaseous atoms, blue arrow there, and then build it all back up again into the new molecules, the red arrow there. Okay, now we know that this particular energy change, they tell us there, that's minus 92. We know that's minus 92. Let's look at the blue arrow then. Here, what are we doing there? We're breaking, well, we're breaking 1 nitrogen, so that's plus 994. 944, sorry. And we're breaking 3 lots of them, so that's plus 3 times 4, 3, 6. And they're all positive values because we're breaking all those bonds. And if we do that, we get a value of plus 2252. On this red arrow, right, what are we doing here? We are forming 6 bonds. So I'm going to call that 6x. And x is going to be the bond enthalpy formation for nitrogen hydrogen bonds. We're forming 6 of those bonds. So Hess's law, we know that minus 92, this one here, is equal to, well, the blue arrow, which is plus 2252, and plus 6x. So rearrange that equation, we get 6x is equal to minus 2344. So x is equal to 2344 over 6. That is equal to minus 391. Now it's got a minus value there because the direction of the red arrow is we are forming bonds. So that's going to be exothermic. So normally if we're asking for bond enthalpies, you don't give it a sign, you just give it a number. So I'd say the bond enthalpy value, the answer to this question is nitrogen hydrogen bond enthalpy is 391 kilojoules per mole. Okay. Right. 4. Give one reason why the bond enthalpy is different from the mean bond enthalpy. Right. So mean bond, the reason why is because this is for ammonia only. It's not the mean, not for a variety of compounds. The mean bond enthalpy is an average value for various different compounds that contain the NH bond. Okay. Whereas you've just calculated the value for ammonia there. Right, so here's a more, this is calorimetry experiment here. Okay. Right, student planned to carry an enthalpy change when magnesium metal here is placed into zinc sulfate solution. You get a displacement reaction. Okay, so what did he do? He got a glass beaker, and that we can probably normally do it in a polystyrene beaker. That's probably going to ask a question about that later on. So we've got a glass beaker there, and we have got 50 centimeters cubed of our zinc 2+ solution, 1 mole per decimeter cubed. And they're going to put 2.08 grams of magnesium into there. And measure the temperature. Okay, so he started off with that temperature and he's finished up with that. Right, first of all, show by calculation which reactant was in excess. Right, so these things, we can see the magnesium and the zinc ions, they react in a 1-to-1 ratio. So let's work out our moles of magnesium first of all. Got 2.08 grams, so moles mg is equal to mass over mr. 2.08 over, which should be AR really because it's an atom, 24.3 for magnesium. That gives us 0.0856 grams. Now let's work out the moles of zinc ions. So we can just do the moles of zinc sulfate because 1 mole of zinc sulfate contains 1 mole of zinc ions. And we are going to they give us the volume and the concentration. So we're going to do concentration times volume, and that's 1 times volume, 50 over 1,000. dm cubed gives us 0.05 moles. Now we can see we've got more moles of magnesium than we have of zinc, so the Mg is in excess. So not all of the magnesium is going to react. Only 0.05 moles, 0.05 moles of the 0.0856 moles is actually going to react there. And we need to remember that in the next bit of the calculation. Okay, so the next bit, what does it ask us? It's going to use the data to calculate the experimental value for the enthalpy of reaction. Okay, so we're going to use two equations here. We're going to use Q is equal to mc delta T, where Q is the quantity of heat released in the experiment. And then we need to convert Q into a delta H in kilojoules per mole. Well, delta H is going to be equal to Q divided by the number of moles. Now, is it the moles of magnesium or the moles of zinc? Well, it's going to be the moles of zinc because the magnesium is in excess and not all of that magnesium is going to react. So let's put moles of Zn2 plus there. Right, so let's do our calculation. Right, first of all, delta T is going to be equal to 61.2 minus 23.9, which is equal to 37.3 degrees C. Okay, so let's work out Q. Right, Q, so M is the mass of the liquid in the beaker here. Okay, and this, so we had 50 centimeters cubed, so that's 50 grams. We're assuming the density is 1 gram per centimeter cubed. So 50 times the specific heat capacity, which is 4.18, multiplied by 37.3. That is going to give us a value of 7,795.7, and that's in joules. Okay, it's in joules because our specific heat capacity is in joules per Kelvin per gram. Okay, now we need to convert that into delta H using this equation here. So delta H is going to be equal to 7795.7 over the moles of zinc, which was 0.05. So delta H is equal to 155,914 joules. So let's convert that into kilojoules, and we're going to go to 3 significant figures because most of our data is up to 3 sig figs. So that's going to be 156 kilojoules. Now, that's really important before we put that in, is that we say that that is minus 156. Why is it minus? Because it is exothermic. Sorry. It's exothermic, right? And if you don't put the minus in there, you will lose a mark. After all that work, you'll lose it for forgetting to put that in. So don't forget, it's exothermic. We can tell it's exothermic because the temperature went up. So minus 156 kilojoules for that, for that reaction. Right. Okay. Another student used the same method, okay, and obtained a enthalpy value of minus 142, and the data book is a lot bigger than that, a lot more negative. Yeah, suggests the most likely reason. Obviously, it is due to heat loss to the environment. Okay, it's always, these kind of experiments are not very accurate because not all the heat goes to increase the temperature of the solution. Right, 3.3. Right, suggest how the student's method and the analysis of the results could be improved in order to determine a more accurate value for the enthalpy of reaction. Right, so don't change, don't refer to the precision of the measuring equipment, and don't change the amounts or the concentration of chemicals. What they're trying to get at here is the way, well, first of all, as I said earlier on, they used a glass beaker, and you wouldn't use a glass beaker, you would use a polystyrene beaker because that is a good insulator. And you'd probably put a lid on the beaker as well, worthwhile mentioning that. Right, so what can you do to improve this experiment without, what else? Well, what they're trying to get at is we go back to required prac 2. And when you work out delta T, it's not a very good idea just to measure the temperature before and then the highest point it gets to. That. So what you should do is you should measure the temperature for 3 minutes every minute for 3 minutes before you add the temperature of the solution, of the zinc sulfate solution, before you add the magnesium. Okay, add the magnesium, say at the 4th minute. You can't measure the temperature then because you're adding the magnesium, and then measure the temperature every minute. For say 10 minutes. And then when you got that, do you remember you plot a graph? And I would probably draw a little sketch graph in your answer. Say plot a graph, and you want to plot on that graph, you want, this is going to be time, and this is going to be the temperature. Right, here's going to be, I would indicate that's before you've, the 3 minutes before you've, of the solution, before you've added anything. It's an exothermic reaction. You're going to add your magnesium there, and you'll find that you'll get a graph something like that. Okay, now this point here, which I'll do in red, the temperature is still rising there because the reaction, the magnesium is still reacting with the zinc, with the zinc solution, and so not all the heat is being released, so that's still going up. But on this part of the curve, it's dropping. The temperature is dropping because the solution is losing heat to the surroundings. So I'd say that. And so what you need to do is extrapolate that line forwards, extrapolate that line backwards, and then you read off the graph at the time you added the magnesium there. That is going to be the delta T. And so this takes into account, you can see there, that the temperature that we're, the highest temperature that would have been the highest temperature if the solution is continuing to lose heat at this rate. That would have been the temperature when you added the magnesium. And this gives you a more accurate value estimation of delta T. Okay. So that required practical, that's come up an awful lot in these past papers. They seem very keen on that. Okay. Number 4, substances P and Q are about equilibrium. So pretend reaction, P and Q giving you 2R, and of course the equilibrium constant, Kc, would be given by that expression there. We should have no problem with that. Okay, 1 mole of P and 1 mole of Q were mixed in a container with a volume of 1 dm cubed. At equilibrium, X had formed. Okay, so you've got to deduce in terms of X the amount of R in the mixture. Now the way I would definitely do that is do one of those little diagrams. So I'll write down P plus Q going to R, and I would do here, I would do start moles, used up moles, and equilibrium moles. So it tells us we start off with 1 mole of P and 1 mole of Q, and we've got 0 R. And it says at equilibrium, we say X of P have been used up. So we've used up X of P. So that means we must have also used up X of Q. So how much P have we got left over? Well, it tells us actually, but it's going to be 1 minus X and 1 minus X of Q. Now, if we've used up X of P, 1 mole of P gives us 2 moles of R. So at equilibrium, we're going to have 2X moles of R. So that is the answer to this question 1.4. The amount of R is equal to 2X moles. Now, the next bit, they tell us the equilibrium constant is 3.6, and they want you to calculate a value for the equilibrium concentration in moles per decimeter cubed of R. Right, so what we should really do here is, well, we need the Kc expression. Kc is, so I should be a 2R there, sorry. Kc is equal to, it's R squared, concentration of R squared, over concentration of P times by the concentration of Q. So really what we need here is we need equilibrium concentration, which is equal to moles over volume. But very conveniently, they tell us here that the volume of the container is 1 dm cubed. So we're just dividing it by 1. So it's going to be, the concentration is also 1 minus X, and 2X there. So we don't have to worry about the volume too much. Right. So we've got to put, now they tell us what Kc is. We've got to put our values into this equation. And the only thing we're going to not know is X. Right. So let's do that. So 3.6 is equal to, well, R is 2X all squared. Yeah, so that would be 4X squared. Yeah, I'll leave it like that. And P is 1 minus X, and Q is also 1 minus X, so that's 1 minus X squared. Now, you can multiply out that equation, and you would get a quadratic equation, and then you could use the quadratic formulae to work out what X is, okay? But there's a quicker way of doing that, and you can see that this is a kind of a perfect square. You can get the square root of that. So we're going to take the square root of both sides of the equation. So we're going to get root 3.6 is equal to the square root of all of that. And you can remember, if you're doing your surds from GCSE maths, that if you do that, you can do 3.6 is equal to square root of 2x all squared divided by the square root of 1 minus x squared. Right, so take the square root of that. That's going to be equal to the square root of 3.6. Well, square root of 2x squared is obviously 2x. And the one at the bottom is 1 minus x. Right, so let us put the numbers in there. So I'll do that on the left-hand side here because I'm running out of space. So the root of 3.6 is equal to 1.89. Is 1.897 is equal to 2x over 1 minus x multiplied, so that's 1 minus x times that. Multiply out the left-hand side. A minute. So we get there. We're going to get 1.897 minus 1.897x is equal to 2x. Take these that onto the other side of the equation. We get 1.897 is equal to 2x plus that gives us 3.897x. So x is equal to 1.897 divided by 3. Which is equal to 0.487. And then you heave a sigh of relief that is less than 1, because it's got to be less than 1, because that is the amount of that's the amount. If you look, what is x? It's the amount of p you've used up, and you started off with 1. Right. The question asks us to work out the equilibrium concentration of R. So the number of moles of R we've got is 2x. So we need to multiply that by 2. Let's do that. So moles of R is 2 times 0.487, which is equal to 0.974 moles. But the question asks us the concentration of R in moles per decimeter cubed. So the volume of the container is 1. So R, the concentration of R, square brackets there, is going to be 0.974 divided by 1, obviously is equal to 0.974 moles per decimeter cubed. Right, that is a pretty unusual question there, because it's a little bit too mathsy for, and it's a chemistry exam, not a maths exam. And you know, if you didn't realize you could take a square root of that, then you spent ages doing the quadratic formula and maybe make a mistake and get the wrong answer. I think there's another one in the specimen papers where they had this, where it works out as a perfect square. But they've only asked it in the specimen paper, and they've asked it in this paper. I don't think they've ever used that. Even on the A-level paper, they haven't done a similar thing to that. It's a bit of a one-off, that question. Right, intermolecular forces now then. Give the meaning of electronegativity. Right, electronegativity is the ability of an atom to attract electrons towards itself, and the crucial bit, in a covalent bond. You've got to have that bit. So you can't really talk about electronegativity unless you're talking about covalent compounds. Okay, explain how permanent dipole forces arise between hydrogen chloride molecules. Okay, so we've got a hydrogen chloride molecule here. Chlorine is considerably more electronegative than hydrogen, so it gets more than its fair share of the electrons in this bond. So it has a partial negative charge, and the hydrogen, of course, will have a partial positive charge. So if you have, so the difference in electronegativity, that's for 1 mark. And so this moment has a permanent dipole. That means the center of positive charge is not in the same place as the center of negative charge. So what will happen is you will get the positive end of one molecule will be attracted to the negative end of the neighboring molecule, and that is what consists the dipole. So for 2 marks there, I think you just got to mention the difference in electronegativity, the fact that you will have a negative end of the molecule and a positive end, and they attract each other. Okay, complete table 4 by naming the shape of each molecule. And place a tick in the final column if it has a permanent dipole. Right, SiH4. Right, silicon is in group 4, so it's going to form 4 covalent bonds, and it won't have any lone pairs. So that means that's supposed to be a dot cross diagram. 4 bond pairs, no lone pairs. That is tetrahedral. And you can see it's going to be perfectly symmetrical, that molecule. I'm drawing it in 3D now. So that means even though the chlorines there are more electronegative and have got a partial negative charge on them, the molecule doesn't have a dipole because they're all kind of pulling against each other. So no tick for that one there. pH3, well, pH3, well, it's very, P is in group 5. Very similar to nitrogen, which is in group 5. Very like, this is like NH3 really, isn't it? You probably remember there that what you're going to have there is you're going to have, so nitrogen's got, and phosphorus got 5 electrons, so we've got 3 bonding pairs. You've used up 3 of the electrons in the outer shell, and you're going to have a lone pair. So that means that is going to be pyramidal, that molecule. So that's P there. So it's like based on the tetrahedron, but you've got the lone pair on the top there. And that molecule is not symmetrical, and phosphorus is more electronegative than hydrogen, so it will have a dipole. And we'll call it pyramidal. Phosphorus is not as electronegative as nitrogen, obviously, because it's one down, but it is pretty electronegative. Beryllium chloride. Now, beryllium is unusual. It's a metal, but it forms a lot of covalent compounds because it's got 2 electrons in that shell. So beryllium chloride is going to be, you're going to have 2 bond pairs and no lone pairs. So the shape is going to be linear. And once again, because it's symmetrical, it will not have a dipole because the chlorines are more electronegative, a lot more electronegative. But you've got delta minus on that chlorine and that one there. They kind of cancel each other out. So no dipole, no tick for that one. CH3Cl. Make a bit of space here, and this one does have a dipole because it is not symmetrical. Right. From a rubber. Okay, so what we're going to have for for the trichloromethane then is we have a carbon. So carbon always forms 4 bonds, has no lone pairs. So we're going to have 3 chlorines, be tetrahedral shape, but 1 hydrogen. Now these chlorines are all very electronegative, and so that means this molecule will have a permanent dipole. So it is tetrahedral, and it does have a permanent dipole. Right, this one now. Copper can be produced from rock, contains Cu, we've got there, CuFeS2. Balance the equation for the 2 stages in this process. Okay, this is a horrendous equation to balance. Okay, so let's have a look at this one here. So we have got, right, we've got two coppers there and 2 coppers there. So we're going to have to put a 4 in front of that. Okay, so that means we're going to have to put a 4 in front of this one here. Now that means we've got 2 sulfurs here. So we've got 8 sulfurs there altogether. 4 lots of 2 makes 8. Right, now we've got 1 sulfur there. So that means we are going to have, let me see. So we've got 8 sulfurs, so we're going to have 7 sulfurs there. Right, now let's count up the oxygens. So on the left hand side of the equation we have got, well, we've got 12 oxygens there, we've got 14 there, and we've got 1 there. That makes 27 oxygens. Oh, right, now before I count the oxygens up, I've got to put a 4 here. I think that works out. We've got to have 9.5 oxygens there. All right. There's no real quick way of doing that. It's just trial and error, really. Okay. This second one's not quite as bad. Right. We have got to have. Right. We've got. Right. We're going to need 2. Right, we've got SO2 there, haven't we? Okay. So we're going to need put a 2 in front of that there. So that means altogether we have now got 6 coppers. So that's 6 Cu and gives us 1 SO2. That will work. 2 reasons why the sulfur dioxide byproduct of this process is removed. Right, the obvious one is SO2, of course, causes acid rain, and so it's got to be removed because otherwise it will cause environmental damage. And the less obvious one is that you can use the SO2, I think, to make sulfuric acid, which can then be sold. So instead of wasting it, you can use it to make something useful. Okay. Right, 6.3. This is a calculation. Not much chemistry in it, but lots of very big numbers. Okay, and plenty of room to make a mistake here. I don't really like this question because there's not, as I say, there's not that much chemistry in it. Okay, so a passenger jet contains 4,050 kilograms of copper wiring, and the rock. Right, okay, you're getting it from this ore, and the rock only contains 1.25% of it. Calculate the mass in tons of a rock needed to produce enough copper wire for a passenger jet. Right, so how much wire we've got? So we've got that many kilograms of copper we need. Okay, so let's work that into grams. So that is equal to times 1,000, 10 to the 3 grams. Now let's work out the number of moles of copper. So that's going to be mass over mR. So this number divided by 63.5 for copper, which gives us 63,779 moles. Okay, now how many moles of the ore are we going to need then? We need that 1 mole of ore contains 1 mole of copper, so moles of ore needed is going to be the same as that number there, 63,779. So the mass of the ore, I shouldn't say ore, I should say the CuFeS2 there. So the mass of CuFeS2 we're going to need is equal to mass times mR, moles times mR, sorry. Now the mR of this, 63.5 for copper, 55.8 for iron, 32.1 for sulfur. That gives you 183.5 is the mR of that. So that's going to be 63779 multiplied by 183.5, which is equal to 1.17 times 10 to the 7 grams of iron, of the copper iron sulfide. Okay, now what we're going to do now is, so that's the mass of the ore we need. Okay, right, sorry, the mass of, okay, now it tells us the rock is actually only 1.5% of this compound. Okay, it's only 1.5%. Now let's say if it was, let's say it was only 1% mass needed of the rock, well, we'd need this number multiplied by 100. If it was only 100 of it was actually that stuff. So let's do that times by 100. So that's going to give us 1.17 times 10 to the 9 grams. But it is 1.5%, not 1%. So mass needed is going to be that. Sorry, not 1.5, it says 1.25. Does it say 1.5 or 1.25? 1 minute. 1.25, okay. So if it is 1.25%, right, if it's 1%, you need that much. If it's 1.25, you'd need that divided by 1.25. So that's going to, and that is equal to 9.36 times 10 to the 8 grams. We need to work that out into tons. Okay, so first of all, let's work that out into kilograms. So divide by 1,000, that's going to be 9.36 times 10 to the 5 kilograms. And then divide by 1,000 again to give us tons. That gives us 936 tons. So that's how many tons of rock you're going to need for the to give you that amount of copper for the plane. Okay, so a lot of numbers there. Okay, right. Copper can be produced by the reaction of carbon with copper 2 oxide according to that equation. Calculate the percentage atom economy. Okay. Right, so atom economy is equal to the mass of the useful product over the total mass of products multiplied by 100. Right, now in this equation we can see we get every time we get 2 moles of copper and 1 mole of carbon dioxide. What is the mass of 2 moles of copper? Is equal to moles times mR, or AR for copper because it's atomic mass. So that's 2 times 63.5, which gives us 127. And then the mass of 1 mole of carbon dioxide is just moles times mR, is equal to 1 times 44 grams. So the percentage atom economy is going to be 127 over 127 plus 44 multiplied by 100, which gives us 74.3%. That's the correct number of sig figs because all our atomic masses are given to 3 significant figures, so we should give our answer to 3 significant figures. Okay, so atom economy GCSE calculation really. Okay, question 7. Okay, this is about group 2 metals. An aqueous solution of Y is known to contain 1 type of group 2 metal ion and 1 type of negative ion. All right. Aqueous solutions of sulfuric acid and magnesium nitrate are added to separate samples of Y. Okay, the observation there. So we add sulfuric. So you've got an M2 plus ion. Sorry, let's call that M2 plus. That's your group 2 metal and another negative ion. Right, sulfuric acid, and you get a white precipitate. That should tell us really that we're probably, this is almost certainly barium. It could actually be strontium as well, because that's not, but strontium sulfate is also very insoluble. But let's say barium. So we're pretty sure that the group, that is Ba2 plus. Now what's the negative ion? Right, so let's talk things. It could be chloride, it could be bromide, iodide, etc. It can't be sulfate, this negative ion. It could be nitrate. It could be hydroxide. Right, now when we add magnesium nitrate, you get a white precipitate. So which magnesium compound is insoluble? Right, magnesium chloride is soluble. You can probably think magnesium hydroxide is very insoluble. So the negative ion is probably hydroxide ion. And just to check that's okay, it says that, we've got this aqueous solution of Y, which we're saying is now it's barium hydroxide. Is barium hydroxide soluble? Well, remember, yes, it is. The group 2 hydroxides become more soluble as you go down the table. Barium's at the bottom, magnesium at the top. So the answer there is that. Now, writing the ionic equation, so for the reaction that takes place when sulfuric acid is added. So it's going to be Ba2 plus aqueous plus sulfate ions, aqueous, goes to BaSO4 solid. You could put in there the, well, I suppose you could write down the full ionic equation if it was barium hydroxide. I don't think you need to though. But if it was barium hydroxide, it would be Ba2 plus 2OH minus, and the sulfuric acid, of course, would be 2H plus and SO4 2 minus, and then you'd also form there, you'd be forming 2 molecules of water, wouldn't you? Okay, but I think just stick with that simplest ionic equation. That is fine. Actually, probably no, because they're not spectator ions here, are they? Because they do actually react, the OH minus and H plus. So yeah, I'd write the top one. So I'll change that. So we want Ba, should put state symbols in, aqueous, OH, aqueous, H plus, aqueous, sulfate, aqueous, goes to barium sulfate solid, and 2H2O liquid. And I think, yeah, I would write the top one, because I say the OH minus and the H plus are not spectator ions. You've got a neutralization reaction going on there. Okay, right. The identity of the negative ion present, we'll sort of explain that, is OH minus. And write an ionic equation for the reaction that takes place when magnesium nitrate is added. So I'll write the full equation, Mg2 plus aqueous. There's going to be 2 nitrates because they're both 1 minus aqueous. We're adding that to barium 2 plus aqueous, 2 OH minus aqueous. We're going to get the precipitate of magnesium hydroxide solid, and left behind you're going to have barium 2 plus and 2 nitrate ions. Okay, now in that case they are spectator ions. The barium and the nitrate ions don't do anything, they are spectator ions, so it'd probably be okay to leave them out of that one and just write the precipitation reaction between the magnesium and the hydroxide. Okay, now that is as far as I'm going to go with that paper. Question 8 I'm going to start in the next video.